for our next talk, I'll invite here on the stage a data scientist at Uber who will talk about why big data didn't end causal inference. I welcome here Totte Harinen.
Thank you. Yeah, my name is Totte. I work for Uber. I assume that many of you know what we're doing. I'm in the Uber Labs team, which is a collection of ex-academics. Our job is to apply behavioral science methods across the business. And for me in particular, I have been working with the Eats business quite a lot, the Uber Eats business, and the rideshare business globally pretty much to trying to use these kinds of methodologies that exist in the behavioral sciences. So I'm going to be talking about causal inference, which also coincidentally happens to be what I have been thinking about for the past 10 years or so. So I did a PhD before coming to Uber here at King's College on related issues, and then I was working for the Consumer Association here for a while, and finally went to Uber about a year ago. And a big part of my job really has been that of thinking different ways of applying causal inference in the business. What I mean by causal inference is very abstract. So it's basically any kind of modeling where some parts of the model are supposed to correspond to a causal structure in the world. So that's a super vague or ambiguous definition of causal inference. Anything from like a randomized controlled trial to quasi-experiments or just like observational causal models would fit this kind of description. Big data, it's even more vague. Lots of observations and or variables per observation. I think that this is probably, I haven't been in this discussion for many years, but I would imagine, and I've seen that this is a big debate in and on itself, what the definition of big data is. So I'm kind of keeping it very vague here. I'm kind of showing my academic background in making this kind of talk to consist of an argument for something against causal inference in the big data era. Then I'm going to discuss some of the reasons why I think it's not such a great argument, and then obviously I'm going to discuss a possibility for reconciliation between those two viewpoints. I'm sure many of you know this article by Chris Anderson, who was the editor of Wired in 2008 when this was published, about the relationship between big data and theory. Basically what he was arguing is that in the era of big data, causal inference or theory more generally doesn't really matter. So basically correlational is fine. You apply an algorithm into a data set, you come up with patterns or rules of association, and that's enough. You don't have to have this kind of old-fashioned view where you have someone thinking about mechanisms like how these variables are connected. Instead, you run an algorithm and you come up with certain patterns. So basically, his idea was that we are moving towards direction where correlation is king. Causal mechanisms, underlying mechanisms don't really matter. I think that there are actually three kinds of considerations. If you read the article in detail, I think there are three kinds of things that he's talking about or kind of referring to, at least implicitly in that paper or article. One is that you could think that humans are bad at coming up with causal hypotheses about the world. That's one possible kind of explanation for or kind of reason for why it would be old-fashioned in a certain way to do causal inference in the era of big data. And it's kind of like that's intuitive to me in a sense, because like you could think that it's we humans are kind of, it's certainly an old way of doing science, right, or analytics. So you come up with some kind of model of the world and then you look at what the data says and trying to compare those two. That's how science has worked for several hundred years. So maybe this area is due for a revolution. That's one possible kind of implicit idea in his article. Another interesting thing that he refers to is that correlational models, so you run some of these algorithms and you come up with certain patterns. So those can be more complex than the kinds of models that we stupid human beings come up with because of our limited cognitive abilities. So the kinds of models, the causal models that you test against data, those kinds of hypotheses, they are abstractions. They are like super abstract constructions of certain variables that we have come up with. And the idea seems to be that you can kind of get past this if you just run an algorithm on data and come up with patterns. So I guess it kind of makes sense. Computers could be better at this kind of these kinds of super complex representations of the reality. And then finally, he refers to this kind of idea that analytics, science, business, those kinds of fields seem to be moving more and more towards the kind of situation where you apply correlational methods essentially into big data sets and come up with interesting patterns. What he's talking about is something related to the clustering of genes, for example. So there are real scientific improvements or scientific progress that's been made by doing this kind of inference. So fair enough, that seems like a good argument. And it seems like these kinds of methodologies are increasing, right? And despite all this, it seems like causal inference hasn't gone away. In science, if you look at published papers, for example, it seems like there are hundreds of them coming out every day that seem to refer to the kinds of causal inference methodologies like randomized controlled trials, obviously, quasi-experiments, causal mediation modeling, those kinds of things. In business and policy, similarly, my experience, for example, during the short time that I was involved here in policy, is that here in the UK, is that the regulators here are really keen to apply causal inference methods from econometrics to basically evaluate regulation, for example. Business, of course, businesses are running A/B tests, quasi-experimental methods, and so on. I will talk about some of the things that we are doing at Uber, which is the last thing here. So obviously, one strand of evidence for me is that we are applying these kinds of methodologies, causal inference methodologies. So on the one hand, we have the kind of prediction from 10 years ago that causal inference is going to disappear in the era of big data, and on the other hand, we have the kind of situation where it just seems that it's thriving. So what are some of the reasons for this? I will discuss three things very briefly, not because they are the kinds of, they are in any way like unimportant, but just because I don't have a lot of time. One kind of thing that I think is quite relevant here, and this is related to kind of research that I used to do in academia, is that humans are actually pretty good at coming up with a causal hypothesis. So in terms of our evolutionary history, it's been pretty useful to be able to answer the kinds of questions of, if I change this, what would happen to this? So that's one thing. Obviously, it doesn't mean that we are good at doing causal inference in a statistical context, for example, or that we wouldn't make mistakes. But still, the idea that we would be somehow bad at coming up with causal hypotheses as such isn't very good. Similarly, one of the ideas that I mentioned that Anderson seems to refer to is that if you have some kind of abstract, complex model, it's better to have the kind of model that is a more accurate representation of the reality. That's complex because reality is as well. On the other hand, I think that abstractness, it's true that these kinds of causal models that we humans come up with about the world are abstractions. But I think there's value to that, which is that one example is that suppose you send an email, for example, to half of your clients, and you have some outcome variable that you're interested in, and then you see a positive relationship between those two in your trial. if you're able to come up with, for example, some kind of abstract psychological model for why your intervention was beneficial, having that abstract model enables you to apply the same learnings in a number of different situations. So that's why I think that it's true that these kind of psychological theories, for example, that you could apply to try to come up with these underlying mechanisms are abstract, but that's also their value. And then there's a more conceptual argument, which is referring to the fact basically that just by looking at observational data without making any kind of causal assumptions doesn't get you into the counterfactual. Counterfactual being the kinds of question of what would have happened in the absence of the cause. That's a counterfactual question because it actually didn't happen. Now you can get to this from observational data alone. I will discuss some of those ways in which you can do that, but you have to make certain causal assumptions of how your observational data relates to the world, which means that just by looking at patterns doesn't get you to that. A couple of things that in my work at Uber, I've certainly noticed are kind of enables better causal inference is the fact that or kind of enables the thriving of causal inference in the big data era is the fact that bigger data seems to enable better causal inference. A couple of examples. If you want to run quasi-experiments, if you want to do like propensity score matching, for example, which is the kind of situation where you have an action, for example, that some of your clients took, and that's not randomized in any way, and then you want to still somehow be able to compare those clients with respect to some further variable down the line with people who would be maximally similar to those people. So what do you do in that kind of situation? How do you identify those people who are maximally similar to those who took this action but didn't take the action? So you could get this kind of like almost randomized type of situation where you can compare those two groups. So propensity score matching or participant matching methods more generally are a way to do this. Why this is easier in the big data era is that you have more variables. So usually you need to have a bunch of variables to be able to predict who are those guys who would have been likely to take this action, whatever it was that you're interested in. Another very almost like trivial example is interrupted time series analysis. So you could have a situation where you change something in your email, as in this example. Like you have a personalized title, for example. You change this at a certain point in your of time. In this case, at the time point 50, whatever that corresponds to. And then you look at your time series. You run some kind of model into that time series to see if there is a statistically significant difference or whatever modeling methodologies you want to use. This is a very like classic almost like old school way of doing quasi-experimental causal inference. You're not randomizing anyone, but you're looking at the time series and seeing if there is a change in the level. Now, why I'm mentioning this here is that it's not trivial to have this kind of time series data where you can do this kind of analysis. So again, based on my experience in policy, it's for policymakers, it's still an issue to have this kind of data where you could use ITS analysis. Whereas for tech companies, it's like you can do this analysis all day long because the data exists. New methodologies as well. The fact that, or the kind of abstract way of describing causal relations has been developed quite recently, which means that many of the kind of computational methods for estimating causal quantities haven't existed actually all that long. Although the concept of causation obviously has been a matter of debate for like hundreds of years, there's really been a revolution in the kinds of computational methods to make causal inference. One example is causal mediation modeling. This is the kind of classical situation where, suppose you have like email send treatment. You send an email to half of your client base again. You want to measure its impact to some post-email engagement variable. You want to measure its impact directly but you also want to measure how its impact is mediated through different routes. Mediation modeling is a way to answer that question. Given certain assumptions, you can quantify the relationship shown here. Now, this is the kind of approach that's become so much easier recently because of the developments in the kind of abstract language of causal inference. So not so long ago, it wasn't, for example, easily possible to run these kinds of models if you didn't have non-parametric data. So this is a good example of the way in which these kinds of methodological developments have enabled something that we couldn't do earlier. Now to the obvious point, is there a reconciliation between these two kinds of approaches? So on the one hand, we had this kind of notion that big data is going to make causal inference disappear, and then we have this development where it seems to be anything but. Of course there is. This is the kind of my kind of ending point here. Some of the reasons why there is a room for reconciliation is that big data, obviously, as I've mentioned several times, enables us to do better causal inference, propensity score matching, interrupted time series, having just more covariates, for example. All this kind of stuff, being able to identify subpopulations or running like multi-arm trials. You have millions of people in your database, in certain cases at least. Similarly, big data findings, if you see interesting patterns, can obviously inform your causal hypothesis. In the eats world, for example, we could be looking at the kinds of restaurants that go together and then running causal experiments using those kinds of patterns that emerge from the data. And then there are very interesting developments where people are thinking about and have already combined some machine learning methods to estimate certain causal quantities. So you kind of explicitly put these two methodologies or approaches together. So in the realm of time series analysis, for example, you could have a situation where you want to predict what the counterfactual time series would have looked like, and you can use machine learning methods to identify certain time series that correlate with the time series that you are interested in. So you can use those to predict what a counterfactual would have looked like. And these kinds of developments are super exciting to my mind because they are kind of explicit recognition of the fact that that these are not causal inference and big data or correlational methods more generally are not in kind of fundamental tension. You can combine the two. So, conclusions. The rumors 10 years ago about the death of causal inference were strongly exaggerated. And it might not have been the case that they were super good arguments, but I think they focused the attention to a very interesting and important point, which is the relationship between these two approaches, because it truly is the case that applying observational or purely correlational analysis is a fundamentally different kind of thing from taking the causal approach, where you make explicit causal assumptions of the world. So that's an interesting question, and I think that's the biggest merit from those discussions. Causal inference, to me, seems like it's here to stay. I have a vested interest here because that's what I have been doing as I said, my basically the last 10 years. There are, ironically, given the arguments years ago, one of the reasons why causal inference is here to stay is specifically because it's now possible for us to do better causal inference thanks to big data. And thanks to all this, my prediction for the future is that the future belongs to both of these kinds of approaches, observational analysis on big data sets, as well as causal inference that kind of goes together with that observational analysis. So that's my bold prediction to end the talk. Thanks very much.
Are there
How far away are we from, if we are, from machines being able to come up with causal inference from big data?
Yeah, that's a very, very interesting question. It depends on who you ask. Some people say that machine learning methods lack the kind of algebra that you need for causal inference. So Julia Pearl, who's been one of the big computer scientists working in this area, has said that he thinks that we need a fundamentally different kind of language to describe causal relations in machine learning models. He hasn't specified the details, so I don't know. But then there are people who argue that the two are compatible, and given that you make certain causal assumptions, you can use machine learning as one of the examples that I referred to is that of predicting counterfactual time series. So those are interesting kind of joint models where you have you make certain causal assumptions of how these variables correspond to the reality, and then you, on the other hand, you have the kind of approach where you're basically just looking at correlations between time series without caring about how the time series data are, what they really correspond to in the world. So they are interesting kind of hybrid models.
I wish all the very best with the outcome of the appeal process that you're making with the TFL. My question is around this causal inference. For example, if you take the subject of entrepreneurship, when you're pitching an idea or when you're making your ideas, then you have some causal inferences. You think that this idea will win. And then as you proceed forward, when you start gathering data, can we use the data, big data, to draw inferences to the basic assumptions you started from?
So I'm not sure if I entirely got the question. So as I said, if you are able to, so if you make certain causal assumptions, then it's legitimate inference. So the way in which I framed the talk was between purely observational, purely correlational analysis, where you really don't make any kinds of assumptions of how the patterns that you see in the data correspond to reality. But then, like many of the modeling approaches, like propensity score matching, for example, there's no intervention there. So it's a purely observational approach. However, you make certain causal assumptions to kind of relate that model to the world. So I'm not sure if this answers your question, but like any kind of, so if you're happy to make causal assumptions, then whether it's big data or small, correlational data can be used to evaluate causal hypotheses. So the kind of tension that I described wasn't so much between experimental and observational data, but rather between purely using purely correlational approach versus kind of making causal assumptions about how that correlational approach relates to the world.
What do you think are some of the most interesting development in causal inference in the last recent years?
Yeah, I think it's the quasi-experimental methods. I think, to me, so like, I think that most companies, businesses, as well as in science, the default method is using randomized trials, where you explicitly, assign people randomly into the treatment and the control. I think that these quasi-experimental methods, I mentioned interrupted time series, propensity score matching or participant matching in general, regression discontinuity as well, which is where you model something and you just try to see if there's a kink or difference in the regression between two variables in the simplest case, are very interesting developments because even if you, like for policymakers as well as in business, it's often not possible to randomize. Or it's not viable. Like if you're doing offline marketing, for example, it's very hard to have the randomized assignment. So any developments in that area, I think, are going to be super valuable because those are the kinds of problems that are very hard to overcome just by trying to design a better experiment. And because my focus is on experimentation, like 90%, I'm very excited about being able to tell my stakeholders that, even if we can't randomize, there's still a way of, doing something better than just like, not doing any kind of causal inference. I think that doing some causal inference is always better than not doing any.
Yeah, can you hear me? Yeah. So I was wondering what your thoughts were on the role and possibly the potential of things like Bayesian networks and network-based or graph theory-based machine learning models, and their potential in the reconciliation of the two approaches.
Yeah, I think this ties back to my answer about or related to Judah Pearl's work, for example. He's obviously advocates a very particular view of causality, which relies very heavily on graphical models. So naturally, there is you start to think about the possibilities, but the honest answer is that I will have to wait for him to solve the issue. I think he's 89 now or something like that. So we'll hope that he manages to solve all these issues during his career. Judah Pearl. Yeah. Thank you.